wrap up clocked circuit, and then get into static RAM, SRAM. Look at some memory circuits. And even though I don't have homework assignments for you guys, but these things will still show up in the final. So I will give you a review on it. So you will make the choice, right? You don't have to turn it in, but you need to know. So there won't be any surprise on the final exam. Let's wrap up this thing. So last time we introduced clock. And we said this is a level triggered D flip-flop. Okay, a very quick review on this. That's a clock bar. It's D, clock bar, clock. Which is Q, which is Q bar? It's being inverted twice, right? That's Q, this is Q bar. All right, so this is level trigger. One quick question. I mean, why do we need this transmission gate? So is that the transmission gate? Or TG? Is that a transmission gate? Yes. So what's a pass gate? Or PG? Just one single NMOS or one single PMOS. That's a pass gate, which is not as good as a transmission gate because for a pass gate, it's either one NMOS or one PMOS. And we know the pros and cons of using either only one NMOS or only one PMOS. And what are they? NMOS is good at passing zeros, and PMOS are good at passing ones. That's why we have complementary MOSFET, which is also called CMOS, right? And because we put all the PMOS stuff on the top to conduct VDD, and we put all the NMOS structure at the bottom to conduct ground. That's why it's called CMOS. We prefer using CMOS instead of just NMOS or PMOS logic. For example, the very old 6502 CPU developed in the 1970s, they do not have CMOS. They have NMOS logic. Can you imagine that? How that works though? They have a pull-up resistor on the top instead of a PMOS. Is that an inverter? 10K? Is that an inverter? If you give a 0, what's the VL here? Yeah. If you give a 1 here, what's the VL? 0. It's an inverter. It is an NMOS logic. It's not a CMOS logic. It still works. But you guys know that the NMOS resistor takes a lot of space instead of just a little PMOS, right? So you prefer a switch, not a resistor on the top. But it can still build logic gates just using an NMOS and transistor. Okay, so this is a pass gate, which is wrong. This is a transmission gate, which is TG, not PG. So why do we need a PG here? TG here. It's testing you guys. Yeah, that's going to conflict with the input over here, right? If you turn this on, why it's going to create a conflict? If you do not turn it on, there will still be something over here. Why it's not conflicting with the input here? But we'll turn it on, it's going to conflict. Why? It's just still that wire, right? I mean, it's not like on or off, but it's going to be something like 2.5 or so. So why it's different? Keep it on or off? Why it's different? So you're passing either one or zeros from the data point, right? So the data is being sent to here and to here. So whenever data is being sent to here, you want this one to be off. So it's not conflicting with the input here. Why? Why when it's off, it's not conflicting? So what is actually affecting this point if you turn it on? Hmm? Hmm? I didn't draw it, right? If you turn it off, then there will be just some residue charges over there. It's very easy to pull it down or up by this very definitive input. Okay, why can you pull it up and down? Because this on and off is there something like either being put up to the, so it's making a path to VDD or ground. So it's very strong source. It's going to do that. If you turn it off, then this one only has some residue charges, cannot determine the logic here, but this will. However, if you turn it on, then you have an inverter here. The inverter is being shorted to either VDD or ground, right? So it's going to be a very strong source. So it's going to compete. That's what's happening. I didn't draw it, but you should know that the inverter has a connection, has a path to either VDD or ground. It's very strong. That's why we sometimes we use the inverter, two inverters as a buffer, because it is able to source current from VDD or ground. It's very strong. Okay, so level trigger. It's a level trigger D flip-flop. Why do we know that? Because when clock is on, whenever D changes, it's going to change your Q. There's no switch in between, right? It's going to change it, which is very bad. We usually prefer edge trigger, not level trigger. So that's why this, is a good example, but not practical. So now let's look at edge triggered D flip-flop. Clock. So why this D flip-flop is a level trigger, edge trigger, not level trigger. So which one's Q, which is Q bar? Figure out that first. Which is Q, which is Q bar. Yeah. Why? Yeah, inverted twice, and Q bar is inverted for 3 times. That's why it's Q bar. And now, let me know if this is a rising edge trigger or a falling edge trigger, or it's a level trigger, and why. So when clock, for example, let's see if this is rising edge triggered, right? If there's a rising edge, so before the rising edge, it's a logic 0, right? So logic 0 will turn this off. So there's no connection from here to here. Okay. So what's happening for this one when it's logic 0 before the rising edge? This is 1, right? This is 1. And this is 0, so the transmission gate here is on. So D will be passed to here. So we're getting a Q bar here. During this period. What about these two? When it's logic 0, this is off, right? So data still passed to here, but not here. So it's not going back, which is fine. I mean, just get the data here. What about this one? This is on, but does that matter for this data here? Why? Yeah, this is off. So why do you need this one to be on whenever this is off? So what's happening here though, if this is on? It's a latch. It's holding that value really steady here. So it's not, and because this is off, so this data, the next data is not affecting this current value as well. However, this latch is going to store the previous value here. Okay, this is a memory. Now let's look at the rising edge. When the rising edge reaches the clock, then this will be off, right? And what's happening here? This is on. And this will be passed to here, becomes Q. And Q will be inverted, becomes Q bar. That's the next Q. Okay. So rising edge is actually a really short period of time, voltage high. So that's why this will be on, and this will be on, but these two will be off. And now let's see, why do we want this one to be off when it's sampling? When this one is sampling. So yeah, so the neural Ds is not going to affect the data at that point. So you can sample just that point. So if D changes, I don't care because I'm only if I can sample really quickly, I will still recover the signal, but I'm not trying to sample everything. So I want to turn off this one. So the rising edge will keep this one on and keep this one on. So why do we need this one to be on? It's a latch, right? So it's going to keep this value steady. It's not changing to anywhere, to anything. We are sampling it. Okay? So why do we want to keep this one off? Yes, it's not interfering with the sample data, right? Okay, so the rising edge, we're good. So we have talked about everything here. So it's going to sample it to Q, no problem. So what about after the rising edge? What's going to happen? And logic high, DC voltage. So it's going to keep these two on and keep these two off. And does that matter, or is that a good thing or bad thing, or it doesn't matter whenever you keep it on? So when we're talking about edge triggered or level triggered, what's the difference? Yeah, after that, right? Or during that period. So the edge triggered after the rising edge, when D changes, Q will not change anymore. But for level triggered, like this one, D changes, Q is going to change. For edge triggered, it's not going to change. So during that voltage high, it's not doing anything except for memorizing this point. So usually, like things like this, I mean, after you sampled it, do you still have to keep it on for a long time? if you have to, right? Otherwise, don't do that. If you have to do it, for example, you are waiting for something else to be done before you sample another one. Otherwise, just keep it short, just sample it. Okay, so what if after? Now let's look at the falling edge. What's going to happen for the falling edge? So this will be off, right? So new data will come in to here. So there will be the next data will come to here, waiting to be sampled in the next rising edge. It's not going to interfere with the current value because this is off. The reason we don't want that one to be changed because what? Because of what? Here in the falling edge. Because we just want to make it to be a rising edge trigger flip-flop. Okay, so it's not going to affect anything. So the falling edge is going to send the new data to here. So what about logic low? Just come back to this point, right? It's the same status with this one. So another waiting for another cycle. So data will sit here waiting for another rising edge and sample this data and send it to here. Is that clear? Well, everything over here? All right. And there are some parasitics of this circuit. You can see there are a lot of gates, which means there are a lot of cox and cox P. So let's take a look at it to see how we can model it. So for the transmission gates, let's think about like if there are any Miller effects going on. So for a circuit like that, how do we model it? Any Miller effect. No, because whenever this is on, this will be on. Whenever this is off, this will be off. So there isn't another source to pull it to a different direction. So what's the cap here? I mean, we split that cap in two halves, right? So the cap here will be cox P over 2. And the cap here will be cox N over 2. Same for the other ones. So what about resistors? So whenever current is being transmitted from here to here, it's running through these channels, not this one. However, the 4 caps are being driven at the same time because they're all shorted to this point, but not the resistors. So the resistor here is being modeled to the following stage, right? So we're only looking at the first stage. And there will be, if you model it, it looks like this. So what is a cap here? Say it again. No, so this whole thing is a model of this thing here. So this point is this point. So what is it? So for each of them, it would be this value. What about the resistor? Got is there a difference whenever it's low to high or high to low? Is there a difference? Okay, so what's a resistor though? What's a resistor you can model here? Whenever the signal is being transmitted from here to here, which one is on, which one's off? They're both on. Is that correct? Yeah, they're both on. It's a transmission gate. You want to turn both of them on. So that's why you want to invert the clock, right? So when they're both on, you got current flow through both transistors. And so what's a resistor here? They're in parallel, right? So what's a resistor? Yeah. Right? Okay, it's the same case for every single resistor over there. Also for the caps. Okay, that's how I model it. Remember how did we calculate the time delay in a circuit like that? We did it for the NL model. And remember that was like 3.4 RC for the total time delay. But just look at your notes. Go back to that lecture. Okay, we did it in the past. If you can model everything like that, the time delay from here to here will be 3.4 N. N is how many stages you have. So 3.4 times N times RC. Okay. One more, the last example for transmission gates. Start with a new page. Pretty big circuits, actually. So for something like that, there are 3 points: D, A, B. So for NMOS, Rn equals to 3.4K, and CoxN is 0.625 femtofarads. For PMOS, our P is same as Rn, and Cox P is 1.25 femtofarads. So find out the time delay from D to A and A to B, and also D to B. So in order to find out the time delay between the 2 points, you want to find out the resistance and parasitic capacitance first. So for the point A, we are looking at point A. What are these caps? Is this on? Yes. So this transmission gate is on. So what is this? A half of cox P. What is this? A half of cox N. And this is off. Is there still a cap? Yes. Do we consider it? No. Why? No, the cap is still there. It won't go through, which means what is what? Why you don't have to consider it? Why you don't need to consider it? So what is zero? Not zero, but disconnect, right? The current is not going through it. Yeah, so I'm thinking like, because cap is still there, but Rn and Rp, so what is that one? Because it's disconnected. Current is not going through. So there won't be any delay to be contributed to the circuit, right? It's like a floating wire, just floating wire, nothing else. So only consider the ones that are on, right? So for the cap, definitely there's these two. So what, no, for the inverter, what are these parasitics? So what is this and what is this? Is there a mirror effect? Not shorted to the, sorry. It's not just shorted to the, if you draw the schematic, right? So the input cap is one here, one here. So it's not just simply both shorted to the VDD, right? So I shouldn't draw that. Okay, it's both. It's adding these two together. So what is the one on the top? So this is cox P, and this is 3/2 of, this is a half of cox P, and this is 1 times of cox P because of mirror effect. So if you add them together, it's going to be 3/2 of cox P. So on the top is 3/2 of cox P. At the bottom is 3/2 of cox N. Okay, so that's everything for this point. So all the parasitics for this point. So for CA, so CA, if we label it as CA, so CA equals 2. So half plus 3/2, so 4/2 will be 2 times cox P and 2 times cox N. So eventually it's going to be 2 times cox P plus cox N. So what about the resistors? Before we do that, let's look at point B first. For point B, there will be a cap here, and there will be a cap here, and this inverter is on, but this is not, so you have to consider a cap here and cap here, and that's it. So this is the input of the inverter, so it's going to be 3/2 of cox P and 3/2 of cox N. So what about this? It's the output of the inverter, so it's only one times of cox P. and 1 times Cox N. So you mean this one? It is contributing because there's no switch, right? Whenever we have done that for the ring oscillator, right? So it's the input, output to the input. So that's why there are, because it's being inverted. No current going that way, but it's going up and down. Okay. So what about CB? Just add all of them together, right? So this is 1 times, this is 3 halves, so we're getting 5 halves. Okay, so now I think we are pretty much ready to calculate the time delay. So what about the delay from A to B, from D to A first, D to A. So delay are they equal? Are they equal? So what are the resistors involved whenever A is oscillating? The parallel resistor over here, definitely, yes. Here, why? So what's the digital model? So now you can find out it's useful, where we didn't waste our time, right? So what's the digital model for the inverter if you draw it? Is there anything in the middle? No. That's the digital model for the inverter. So we are looking into that direction. It's getting into there, right, in input. There's no resistor involved. It's disconnected. It's a gate. So are they equal? Yes, because they have the same resistor, which is Rn in parallel with Rp. Equals to what? 0.7 times Rn in parallel with Rp times what? Ca. Done for point A. So what is delay from A to B? Start a new paper. From A to B, look at B. So the output definitely has resistors involved, right? Whenever it's L to H, Rp is involved, H to L, Rn is involved, and there's nothing involved. So TPLH, TPHL, they're not equal. So TPLH equals to 0.7 times what? Times CB. Oh, LH pulling up. Okay, that's delay from A to B. So what about the delay? Final question, the propagation delay. From D to B, from D to B. So I have to label it as TPHLA, TPLHA, and this is B. So yeah, TPLH equals to yeah, A plus B. So I'm thinking now is inverted, right? I mean, should we add LH to HL, or we're looking at the point here, B, right? Whenever this guy is from L to H. And this is definitely from H to L. I didn't get that. Say it again. Oh yeah, that's true. I think so. So because here and here is the same, right? You can consider this to here is the same point. It's not being inverted. When you're looking at this one, you just add TPLH A to TPLH B. Like that. Agree with that? All right. Okay, let's look at the memory circuits, which is the fun part. There are several terms in the memory circuits: SRAM, DRAM, SDRAM, ROM, Flash, sorry, EROM, EEROM, oh no, EPROM, sorry. Sometimes it's also labeled as E square PROM. So what are these? It's a little bit overwhelming. So what is SRAM? So what is RAM? Random access memory. So we'll learn how to build it in FPGA in the next semester. So random access memory, is that volatile? What does that mean? Yeah, if you power it off, you lose everything. It's like the memory card you have on a computer. You turn it off, there won't be anything there anymore, right? It's be blank. And is it programmable? Can I write to it? Can I read from it? Can I write to it? Yes. Can I read from it? Yes. It's gonna be ridiculous if you write to it but cannot read from it. Why do you write to it? Just for fun, right? Mm-hmm. So what is SRAM? Static RAM. So we'll introduce the SRAM circuit if we still have time, okay? And we'll do a simulation on it. So what is DRAM? Dynamic RAM. And what is SDRAM? Static and dynamic RAM. No. So what is SDRAM? Is that a DRAM or is it SRAM? It's a DRAM. So S is not static anymore. So S means synchronous. So what is ROM? Read only? So a question, read only, so cannot write to it. So what are in there? Yeah, pre-stored in there, right? So, from the manufacturer. So flash memory is different. So flash memory can be, if you turn it off, still there, like USB drives. If you turn it off, still there. There's no power, there's no battery in the USB drive, right? So data can still store there. But you have to know that for a flash memory, it's not a permanent way to store data. So seems like the data can stay on the USB drive for a very long time. It's not forever. The charges are leaking, so very slowly, but yes. So after 20 years, probably the data is not, permanently there anymore. But you have to, whenever you plug in, so your computer will charge it up. If you do not use it and put it in the drawer for 20 years, there might be something wrong after that. But if you plug in anytime during that 20 years, it's going to be charged up and keep the data there very strong. So keep in mind, USB drive is not a permanent device to store data. And EROM, erasable ROM, so you can erase the data in ROM and then reprogram it. I don't know, it's just EROM, erasable. I mean, didn't say P. If you have a P here, it's an erasable and a programmable ROM, right? So you can, whatever, in the ROM, you can erase it or can program it. I mean, the reason it has an E here is because it's electrically erasable and programmable. So what's the difference? Because in the old days, people use laser to erase the data. So they put the ROM under the microscope and use laser pointers to damage, to disconnect the wires, to burn it, to blow it up, to reprogram that ROM. So it's very inconvenient and it doesn't exist anymore. So right now the ROMs are not really ROMs anymore because they are electrically erasable and programmable. It's not read-only anymore. You can even write to it because it's erasable and programmable. Whenever you're programming that ROM, you're actually writing to the ROM. Okay, so they're not, you know, ROM anymore, but still, it's still called ROM. So these are pretty much everywhere. So all the microcontrollers used E2PROM to store the program, like you program into Arduinos, they were stored over there. And so whenever the CPU can send an address to the ROM to take out the instructions. So whenever you write a code in Arduino, for example, you assign a number to a variable, right? That's an instruction. That's a very high level sketch written in C++. However, that one, if you convert it, so whenever the compiler compile it, it converts that C++ code into, can be something in the middle, like assembler or something, and then eventually becomes a machine code, which are just ones and zeros. And these ones and zeros will be stored in the ROM, like instruction. Okay, so that's the instruction. So you have a place to store the instructions, which is code you write into your EDA tools. And there's still a place to store the data, right? The data memory or instruction memory. So the instruction memory store all the instructions, and the CPU will send the address to the ROM to take out every single instruction and use these ones and zeros to turn on all of the registers in the CPU to do something. Okay, that's how that works. So there's an address for instructions, also address for the data. And that's how you control it. And there are several main players in this industry, not too many actually. So the most important one, the biggest ones, not one probably. So for example, Micron. I'm sure I've heard about it. Where is Micron? Boise. Where? Where is Boise? Yeah, and Samsung is another main player in the industry, in the memory industry. South Korea, right? And what are these DRAM manufacturers that I've heard of when you're assembling a computer yourself? Kingston. Have you heard about that company, Kingston? Is that a memory manufacturer? They just assemble PCBs. If you look at the Kingston's DRAM card for desktop, look at the chip on the top of the chip. Usually it's either Micron or Samsung. So they are making PCBs. So they're not getting the major profit from this industry. So who are getting the most profit from it? These ones. That's why the IC industry is a core competency of the country. It's very important. So there are some DDR, when we are looking for RAM cards from Amazon, so you'll see the names are like DDR1 until DDR what right now? 5. So DDR5 is the 5th generation of the DDR memory. So what is DDR? What does DDR mean? It's a double rate, double data rate. So DDR, something they didn't usually they didn't mention it, but it's DDR SDRAM. And you know what is SDRAM? So the RAM card being used in the laptop or desktop, these are DDR SDRAMs. So are SDRAMs dynamic RAM or static RAM? Dynamic RAM. Okay. Double data rate, which is DDR. So when DDR5 was available on the market, just last year. So if you're trying to look for DDR RAM cards on Amazon, you know, try to pick up DDR5. Because they're not as expensive as last year, because right now it's already 1 year old. Definitely they will be faster and better quality compared to all the other ones. But you can look at it, whenever DDR5 becomes available, DDR4 will be dirt cheap, right, compared to a few years ago. It's very cheap right now. Okay, so introduce the IC RAM circuits on Friday. Okay.